Welcome back, and the topic for today's video is an explanation of how buffers work. So let's just first quickly review our definitions of buffers that I gave you in class. We know that the working definition of a buffer is that it's a solution that's going to resist the change in pH upon addition of a strong acid or a strong base. But then we also have the second definition, which is the chemical definition of a buffer, which states that a buffer is going to be a mixture of a conjugate acid-base pair in large excess relative to the concentration or amount of acid or base to be added to the buffer. So what we want to talk about today is how a buffer actually does its job. So let's talk a little bit about a specific buffer. So first, I've got a solution here that's going to be a mixture of a weak base, ammonia, at 1 molar concentration, and its conjugate acid, which is going to be ammonium ion. I could have actually brought that into solution as a salt, such as NH4Cl. Okay, that would be a solid. I could actually dissolve that into the solution to give me 1 molar ammonium ion. So this satisfies our chemical requirement of a buffer because this solution does indeed contain a mixture of a weak base and its conjugate acid in large concentrations. So the question now becomes, for this particular buffer solution that I've set up, how would it respond to addition of acid or base? So in our case, as an example, we want to add some HCl. In a secondary example, we want to add some sodium hydroxide. Both of these are strong components. HCl is a strong acid, NaOH is going to be a strong base. So we know that when they dissociate into solution, the HCl will be a good source of hydronium ion, and the sodium hydroxide, of course, will be a good source of hydroxide ion. So I'm actually going to use those ions as a description of the chemistry that goes on. So let's take a look at each individual case. The first thing I'm going to do is to add the hydronium ion. So what we're going to get is this reaction over here. So the question I have to ask myself is, if I add hydronium ion as the acid, which component of the buffer solution is it going to react with? We really have two choices, right? We have the base component or we have the acid component. So if I'm adding an acid as hydronium ion, it seems reasonable to suggest that that is going to react with the base part of the buffer. Okay, so let's show that chemistry. So here's the acid that I'm adding. It's reacting with the 1.0 molar base component of the buffer. And what we're going to get is a reaction that we can assume goes 100% to the right because it has a very large equilibrium constant, as I'm going to show you in a moment. So it's a Bronsted-Lowry acid-base reaction where the H3O1 plus is going to be my acid. It's going to protonate my base. What I'm going to make is the conjugate acid, which is going to be the ammonium ion, and the conjugate base, which is water in this case. Now this is a little bit different reaction than we've seen before, because normally we would show an acid or base reacting with water. But in this particular case, we have the acid reacting with a weak base, ammonia. Now, why do I assume this reaction goes 100% to the right? Well, the reason for that is because it has a large equilibrium constant. So that's the assumption I can make. Now, if you look at this thing, the K for this reaction is actually going to be 1 over the Ka reaction for the ammonium ion. And you can see that by looking at the reverse reaction. If I have ammonium reacting with water to give me ammonia and hydronium ion, that's the Ka reaction for the ammonium ion. All right? So if I flip that reaction as I have it here, that's 1 over the Ka for the ammonium ion. Ka for ammonium ion is a very small number. 1 over a very small number is going to be a very large number. So for our first approximation, we can assume that this reaction goes 100% to the right. Another way of stating this as a rule of thumb is if you have a strong component, like hydronium ion, reacting with a weak component, such as ammonia, we can make the assumption that the reaction goes 100% to the right. So weak plus strong goes 100% to the right as a first approximation. Now let's take a look at what happens if I add sodium hydroxide, where hydroxide, of course, is going to be a strong base. Now in this particular case, the strong base is going to want to react with the acid component of the buffer. If if we look at this, the acid component of the buffer is going to be the conjugate acid of ammonia, which is the ammonium ion. We know that that's going to be a weak acid in solution. So we let the hydroxide ion react with the ammonium ion. Again, this is a situation where we have a strong component reacting with a weak component. So strong plus weak goes 100% to the right. Again, we can verify that. It's just a Bronsted-Lowry acid-base reaction, where now the ammonium ion is the acid, hydroxide will be the base. So the ammonium ion will protonate the hydroxide. We're going to end up getting ammonia as the conjugate base and water as the conjugate acid. And again, we can see here that we're going to get a large K for this, because the K for this reaction is going to be this reaction in reverse, which happens to be the Kb reaction for ammonia dissociating in water. So we know that that Kb is something on the order of about 10 to the minus fifth. 1 over that is going to give me a large number, something to the order of 10 to the fifth. So we can assume this reaction goes 100% to the right. So again, the take home of this particular part of the video is that we want to see that whatever acid we add to the buffer will react with the base part of the buffer. And if we add a base to the buffer, that's going to react with the acid part of the buffer. And as a result, we're going to end up shifting these concentrations ultimately of ammonia and ammonium ion, and then ultimately we can determine a pH based upon the shifts in those particular concentrations. And that's the next thing that we're going to talk about. So the next thing that we want to do is we want to show you a nice simple equation that we can use to calculate the pH of a buffer before we actually adjust the pH of the buffer. So normally speaking, if we were in an application where we'd use a buffer, we want to prepare that buffer to a particular pH first. Then in a secondary set of steps, we worry about what would happen to the pH of the buffer if we were to add an external acid or base to it. So we first want to look at an equation that we can use to set up the initial buffer at a given pH. So that equation is called the Henderson-Hasselbalch equation. And again, we need to be careful to use it only if we know that we are dealing with a buffer, as in preparing a buffer or using a buffer. All right, so it's used to quickly and conveniently calculate the pH of a buffer solution as we make it up. So let's quickly derive the Henderson-Hasselbalch equation so we can see where it comes from. So I'm going to start out with a simple weak acid dissociation reaction governed by a Ka, as we see here. So here's my generic weak acid reacting with water to make hydronium ion and the anion of the acid. So we obviously have a conjugate acid-base pair here. So here's the acid, and the A1 minus would be the conjugate base of the acid. So we have a conjugate acid-base pair here, which is what we need to have for a buffer. So now I can set up a Ka expression for this, products over reactants according to the law of mass action. And now what I'm going to do is I'm going to take the negative log of both sides of this particular equation. So we see that when I do that, I get the negative log of the Ka is equal to the negative log of the ratio of the products to the reactants. Now if I look at this, I see that anytime I put a negative log in front of anything, I know that that means that I use a P. Okay, so a pH, of course, means the negative log of the hydronium ion concentration. So in this case, I have the negative log in front of the Ka, so I can call that a pKa. It's just another way of stating that I have the negative log of the Ka. Now, the other thing I can do is I can separate the log into, or the argument of the log into two terms. So I'm going to separate out the hydronium ion concentration here. So I can take the negative log of the hydronium ion concentration, so pKa is equal to the negative log of the hydronium ion concentration plus the negative log of the anion over the acid. All right? So that's what I have next. So now what I have is a situation where we should be able to recognize that the negative log of the hydronium ion concentration is also equal to pH. So now my equation condenses into pKa equals pH minus the log of the anion over the original acid concentration. So now I'm just going to rearrange that equation to solve for pH. And when I do that, I end up with pH is equal to pKa plus the log of the ratio of the anion over the original acid concentration. That's the Henderson-Hasselbalch equation. Now, in a general most form, we often say that pH is equal to pKa plus the log of the base part of the buffer divided by the acid part of the buffer. And another thing to remember when we use Henderson-Hasselbalch is because we're looking at a log of a ratio here, we can either use molar concentrations as specified, or if it's easier to solve the problem, I can actually use moles of base over moles of acid if I wish to do that. So that's Henderson-Hasselbalch equation, and again, we can use that in a very simple sense to be able to calculate the pH of a buffer. Or if we want to know the amounts of the anion or acid relative to one another to make the buffer to a given pH, we can use Henderson-Hasselbalch to do that as well. So we're going to find that it's a very, very convenient equation to use for setting up a buffer solution. And that's where we'll start in class next time. See you next time.